In a university lab in Hong Kong, a team of mechanical engineers built something that shouldn't exist yet, a cooling device with no compressor, no refrigerant gas, and no volatile chemicals of any kind. Instead of pumping a synthetic gas through copper lines the way every air conditioner on Earth has done for over a century, this machine cools a room by squeezing and releasing tiny tubes of metal, nickel titanium alloy, thinner than a drinking straw, arranged in bundles so compact the entire active cooling mass weighs less than the phone in your pocket. And in a test published in the journal Nature, one of the most selective scientific journals in the world, that device brought a small room from over 30 degrees Celsius down to a comfortable 21 degrees in 15 minutes flat. No hum, no refrigerant, no greenhouse gas leaking slowly into the atmosphere over the machine's lifetime. If this technology scales, the air conditioner mounted on your wall right now, the one rattling through every summer, cycling refrigerant that is hundreds of times more potent than carbon dioxide as a greenhouse gas, could eventually become a relic. Not tomorrow, not next year. But the physics is no longer theoretical. It has been demonstrated, measured, peer-reviewed, and published. Here's how it actually works, why it took decades to reach this point, and why turning it into a product you can buy is harder than it sounds. Stop for a moment and think about how many machines around you right now are quietly doing the same job. The air conditioner cooling your living room, the one mounted outside a restaurant kitchen, the one inside the server room keeping a data center from overheating, the one in your car's dashboard, the one inside a hospital keeping operating rooms at a precise temperature, the one preserving medication at the pharmacy down the street. According to the International Energy Agency, there are well over 1.5 billion air conditioning units installed in buildings around the world right now, and that number is projected to grow to 5.6 billion by 2050. That means roughly 10 new air conditioners are being sold somewhere on Earth every second. Every single one of them, regardless of the brand name on the front, runs on the same fundamental principle. Compress a refrigerant gas until it heats up. Push it through coils where it dumps that heat outside. Let it expand and cool down, then run it past indoor air to absorb warmth from the room. Repeat. Over and over, thousands of cycles a day. This process is called vapor compression refrigeration, and it was first applied to comfort cooling by an American engineer named Willis Carrier in 1902. He designed it originally to solve a humidity problem at a printing company in Brooklyn, New York. The ink kept smearing because the air was too moist. Carrier's system circulated air over coils filled with cold water to pull moisture and heat out of the room. It worked. And from that point forward, the same underlying thermodynamic cycle, compress, condense, expand, evaporate, has powered virtually every cooling system built anywhere on the planet. That was over 120 years ago. Since then, humanity has split the atom, sequenced the human genome, landed rovers on Mars, and built artificial intelligence capable of writing and reasoning. And yet the machine keeping your bedroom cool on a hot night still runs on the same basic loop Willis Carrier used to stop ink from smearing in a Brooklyn print shop. The components have gotten better. The efficiency has improved. The refrigerants have changed names. But the core mechanism, a compressor squeezing a chemical gas through a closed circuit, has not fundamentally changed. And here's the part that rarely gets mentioned in the brochure. That compressor is the single most mechanically stressed component in the entire system. It runs constantly under high pressure, its internal pistons or scrolls cycling thousands of times per hour, generating vibration, friction, and heat with every revolution. That's the hum you hear through the wall at night. It's also the primary reason air conditioners eventually fail. The compressor doesn't just wear down, it accumulates microscopic damage on every cycle until one day, years down the line, something inside it gives. And when the compressor dies, the entire system dies with it. That repair bill, or more often, full replacement, is one of the most expensive maintenance events most homeowners face, and the refrigerant gas sealed inside the system is not harmless. According to the International Energy Agency, cooling already accounts for roughly 20% of all electricity used in buildings worldwide. The IEA's Future of Cooling report projects that global energy demand from air conditioners could triple by 2050, requiring new electricity generation capacity equivalent to the combined power grids of the United States, the European Union, and Japan. And then there's the chemical side. Most residential air conditioners today use hydrofluorocarbon refrigerants, commonly known as HFCs. HFCs don't damage the ozone layer the way older refrigerants did, but they are potent greenhouse gases. According to the Climate and Clean Air Coalition, some common HFCs have a global warming potential hundreds to thousands of times greater than carbon dioxide. The Kigali Amendment to the Montreal Protocol, adopted in 2016 and ratified by more than 170 countries, commits the world to cutting HFC production and consumption by more than 80% over the next 3 decades. If fully implemented, that single agreement is projected to prevent up to 0.5 degree Celsius of global warming by the end of the century. That tells you something about the scale of the problem these chemicals represent. So you have a machine that accounts for a massive and growing share of global electricity demand, depends on a compressor that mechanically degrades over time, and relies on a chemical refrigerant the entire international community has agreed to phase out. That's the machine sitting in your wall right now. And researchers have known for a long time that a fundamentally different approach was needed. The question was never whether the physics existed, it was whether anyone could make it work at a scale that actually mattered. Here's where the story shifts. There's a physical phenomenon that scientists have understood for over a century, but have only recently figured out how to harness for real-world cooling. It's called the elastocaloric effect. And the simplest way to understand it is to try something you can do right now. Take a thick rubber band, stretch it quickly, and press it against your lip. You'll feel it get slightly warm. Now let it snap back to its original shape and press it to your lip again. It feels cooler. That tiny temperature shift you just felt is the elastocaloric effect. Certain materials, when you mechanically stress them, release heat, and when you release the stress, they absorb heat from their surroundings. In a rubber band, the effect is barely noticeable. But in a class of metals called shape memory alloys, the effect is dramatic. The most studied of these alloys is nickel titanium, commonly known as nitinol. When you compress or stretch nitinol, its internal crystal structure undergoes a reversible phase change, shifting from one arrangement called austenite to another called martensite. That transition releases a measurable burst of heat. When you release the mechanical stress, the crystal structure snaps back and the material absorbs heat from whatever is around it, effectively cooling its surroundings. This isn't a subtle laboratory curiosity. According to published research, nickel-titanium alloys can release between 20 and 30 joules of heat per gram during this transformation. And because the phase change is fully reversible, the material can do this over and over, thousands of times, without degrading the way a compressor's mechanical parts do. Scientists have known about this effect for decades. Researchers at universities in Germany, Italy, Slovenia, and the United States have all built small prototypes demonstrating that shape memory alloys can produce a cooling effect with no refrigerant and no vapor compression cycle at all. The World Economic Forum listed elastocaloric cooling among its top 10 emerging technologies in 2024, and the European Commission has recognized it as one of the most promising alternatives to conventional heating and cooling systems. But there was a persistent problem. Every prototype built before 2025 was too weak. The maximum cooling power any elastocaloric device had achieved was around 260 watts. That's enough to cool a mini fridge, not a room, not a house, not anything close to the kilowatt scale output required for a real air conditioner. The technology worked in principle, demonstrating, but it couldn't produce enough cooling power to compete with even the smallest residential vapor compression unit. That barrier stood for years, until a team in Hong Kong broke through it. In early 2025, researchers at the Hong Kong University of Science and Technology, known as ECKIOST, published a paper in the journal Nature titled "Achieving Kilowatt-Scale Elastocaloric Cooling by a Multi-Cell Architecture." The research team, led by Professor Sun Qingping and Professor Yao Shuhai from the Department of Mechanical and Aerospace Engineering, identified that 2 specific engineering bottlenecks had held the technology back. First, previous devices couldn't balance the cooling power of the refrigerant material with the total mass needed to produce a useful amount of cooling. In simple terms, you either had a tiny amount of alloy that cooled efficiently but couldn't move enough heat to matter, or a larger mass that was too sluggish to cycle quickly. Second, the heat transfer between the alloy and the surrounding fluid was too slow during high-frequency operation. To cool a room, you need the material to cycle rapidly, absorbing and releasing heat many times per second. But if the fluid carrying that heat away can't keep up, the whole system bogs down. The ECKIOS team's solution was an architecture they call SMAs in series, fluid in parallel. They connected 10 individual elastocaloric cooling units end-to-end along the direction of mechanical force. Each unit contains 4 thin-walled nickel-titanium alloy tubes. The entire active cooling mass across all 10 units totals just 104.4 grams. That's less than the weight of a typical smartphone. The thin-walled tubes have a high surface area-to-volume ratio, which means heat can move in and out of the metal quickly. And instead of circulating all the fluid through a single path, the team ran parallel fluid channels alongside the units, keeping the internal pressure below 1.5 bar. That low pressure means the system can operate at high frequency, cycling 3.5 times per second, without the fluid channels becoming a bottleneck. But they didn't stop there. The team replaced the distilled water that previous designs used as a heat transfer fluid with something more effective, graphene nanofluid. At a concentration of just 2 grams per liter, this graphene-infused fluid conducts heat 50% more efficiently than plain water. And because the graphene nanoparticles are just 0.8 micrometers in diameter, far smaller than the 150 to 500 micrometer width of the fluid channels, they flow freely without clogging. The result, a device that achieved a specific cooling power of 12.3 watts per gram, nearly 3 times the previous record for any liquid-based elastocaloric system, and a total cooling power of 1,284 watts. That's the first time any elastocaloric device has crossed the kilowatt threshold. To put that in practical terms, the team tested the device on a small model house with a volume of 2.7 cubic meters in an outdoor environment where temperatures ranged between 30 and 31 degrees Celsius. The device brought the indoor temperature down to between 21 and 22 degrees in 15 minutes. No compressor, no HFC refrigerant, no ozone risk, no greenhouse gas trapped inside the system waiting to leak, just metal tubes being mechanically compressed and released, over and over, with a thin film of graphene-enhanced fluid carrying the heat away. Quick question before we continue. If a cooling system like this, completely silent, no refrigerant, no compressor hum, ever reached your local appliance store, would that change what you buy? Or does price still determine everything? Drop your answer in the comments. And if you're finding this kind of deep explanation valuable, hitting like and subscribing genuinely helps this channel keep making these videos. Now, it's important to understand what the HKS team built in context, because this research didn't emerge in isolation. It's part of a broader global effort to replace vapor compression cooling with solid-state alternatives, and multiple teams around the world are racing toward the same goal, using the same fundamental physics. At Saarland University in Germany, Professors Stefan Sielecki and Paul Motzke have spent years developing their own elastocaloric cooling prototypes. Their approach uses bundles of ultra-thin nitinol wires, each about 200 micrometers thick, roughly the width of 2 human hairs, stretched and released inside a rotating circular cooling chamber. Their prototype mini-fridge, demonstrated at the Hannover Messe Industrial Technology Conference in 2025, can reach temperatures as low as 15 degrees Celsius inside the cooling chamber. The Saarland team's approach is different in design from the HKS system, using tension on wires rather than compression on tubes, but the underlying physics is identical. Stress the alloy, it heats up. Release the stress, it cools down. Professor Sielek has described the nitinol wires his team uses as artificial muscles because the alloy remembers its original shape and snaps back to it after being stretched, just like a muscle contracting after being extended. He has been quoted stating that the efficiency of elastocaloric materials is more than 10 times that of today's conventional air conditioning systems at the material level. And his team is now part of an EU-funded project called SMECOOL, which is specifically aimed at developing a residential elastocaloric air conditioner. The project also includes researchers from the University of Naples in Italy, the University of Ljubljana in Slovenia, and the Irish company Exergen, which is building a heat pump that uses nickel-titanium plates compressed hydraulically. This isn't a single lab working on a curiosity. This is a multi-continent, multi-institution engineering effort with dedicated public funding, published results, and prototype hardware. But here's the part that matters most, and the part that most videos about emerging technology tend to skip over entirely. Let's be honest about exactly where this stands right now. The HKS device is a laboratory prototype. It cooled a model house, not a real apartment. The 2.7 cubic meter test enclosure is roughly the size of a large closet, not a bedroom or a living room. Scaling that performance from a closet-sized space to a typical residential room, let alone an entire home, introduces a completely different set of engineering challenges. Heat loads in real buildings are uneven. Walls absorb and re-radiate heat. Windows let in solar radiation. People, cooking appliances, and electronics all generate heat that the cooling system has to overcome continuously. None of those real-world variables were present in the controlled test environment described in the Nature paper. Then there's the material cost. Nickel-titanium alloys are significantly more expensive than the HFC gases used in standard air conditioners. The alloy must be manufactured to precise specifications. It has to withstand millions of compression cycles without fatigue cracking. And while the HQ's team confirmed through X-ray tomography that their tubes maintained structural integrity under 950 megapascals of stress, long-term durability testing over years of continuous residential use is a different standard entirely. Then there's manufacturing. Vapor compression air conditioners are manufactured on a massive global scale, millions of units per year. The supply chains, the factories, the trained technicians, the installation infrastructure, all of it exists and has been refined over decades. An elastocaloric air conditioner would need an entirely new manufacturing and installation ecosystem built from the ground up. That doesn't happen quickly, and it doesn't happen cheaply. Professor Sun Chingping himself acknowledged this when he stated that his team is working with industry to drive the commercialization of the technology. But working toward commercialization and having a finished product on a shelf are two very different things, separated by years of engineering, testing, regulatory approval, and cost reduction. There is no announced price. There is no announced release date. There is no finished consumer product. And yet, the reason this research matters isn't because a product is about to arrive. It matters because a barrier that stood for decades just fell. Before the HQ's paper, no elastocaloric device had ever produced a kilowatt of cooling power. That number was the threshold the field needed to cross to even begin a serious conversation about replacing vapor compression air conditioning. Now, that threshold has been crossed. And it was crossed not by a marginal improvement, but by a factor of nearly 5 over the previous best, from about 260 watts to over 1,184 watts in a single architectural redesign. That kind of jump tends to attract investment, engineering talent, and institutional attention in ways that incremental progress does not. And the timing matters. The Kigali Amendment is now ratified by more than 170 countries. The global regulatory pressure to move away from HFC refrigerants is real and accelerating. According to the Climate and Clean Air Coalition, without action, HFC emissions were on a trajectory to double every 5 to 7 years. That regulatory momentum creates a market pull. Companies and governments actively searching for cooling technologies that don't rely on gases the world has agreed to phase out. And right now, elastocaloric cooling is one of the very few solid-state alternatives that has demonstrated real cooling at a meaningful scale. Here's the broader picture. This isn't just about one invention in one lab. What's happening across elastocaloric research, from Hong Kong to Saarbrücken to Naples to Dublin, mirrors a pattern that's been repeating across several everyday technologies in recent years. The refrigerator, the microwave, the dishwasher, the light bulb, the internal combustion engine. One by one, machines that ran on the same core principle for 50, 80, or 120 years are being quietly re-examined by engineers who asked a simple question: what if the fundamental approach itself is the problem? Not the efficiency of the compressor, not the chemistry of the refrigerant, but the entire idea of compressing a gas through a sealed loop to move heat. In the case of cooling, the elastocaloric approach doesn't just swap one refrigerant for a less harmful one. It eliminates the entire category of refrigerant. It eliminates the compressor. It replaces a chemical process with a mechanical one, grounded in physics that has been understood for over a century, but that has only now been engineered into something powerful enough to matter. That's a fundamentally different kind of shift than making a slightly better version of the same machine. And if the engineering continues to close the gap between laboratory result and commercial product, which is the hard part and could still take years, it wouldn't just affect the air conditioner in your home. It would affect the cooling systems inside electric vehicle battery packs, the thermal management in data centers running artificial intelligence workloads, the portable cooling units used in field hospitals, and the cold chain infrastructure that keeps vaccines viable across the developing world. Every one of those applications currently depends on vapor compression. Every one of them faces the same fundamental constraints: a compressor that wears out, a refrigerant that leaks, and an energy bill that climbs as the planet warms and cooling demand accelerates. A solid-state alternative with no compressor to fail, no chemical refrigerant to regulate, and the potential for higher energy efficiency at the material level wouldn't just be an upgrade, it would be a category shift. It would change the economics of cooling in tropical countries where billions of people still lack access to air conditioning. It would change the design constraints for electric vehicles, where every watt spent on cabin cooling is a watt that doesn't go to the wheels. And it would change the operating costs of data centers, where cooling is already one of the largest single-line items on the electricity bill. It's a strange thing to sit with. The air conditioner on your wall right now, humming through another summer, runs on the same thermodynamic loop that Willis Carrier sketched on a train platform in Pittsburgh over a century ago. And in laboratories on opposite sides of the world, engineers are squeezing tiny tubes of metal and watching them pull heat out of a room with nothing but physics and careful architecture. The wall hasn't fallen yet. The product doesn't exist yet. But the barrier that kept this technology out of serious contention for decades has just been broken. And for the first time in the history of mechanical cooling, the question is no longer whether a compressor-free air conditioner could work. The question is when the engineering, the manufacturing, and the economics will catch up to the physics that already does. So here's what I'll leave you with. How many other machines around you right now, the ones so ordinary you've stopped noticing them entirely, are sitting on the edge of being quietly replaced by something built on physics that already exists but hasn't been engineered into a product yet? Let me know what you think in the comments. And if you want to keep learning how everyday technology is being reimagined from the ground up, subscribe so you catch the next one. I'll see you there.